Hey everyone, and welcome. Today, we're going to dive into one of the oldest, most reliable, and honestly most important building blocks in all of software, the array. It's truly the foundation for how we handle data, so let's get right into how it all works. But first, let's start with a really basic question. You know, when you save a photo, or load up a game, or even just type a simple sentence, how does your computer actually remember any of that? What's really happening under the hood? Well, the answer starts with a structure that's surprisingly simple. Now, to really get a gut feeling for how arrays work, we're not going to start by looking at a bunch of complicated code. Nope. Instead, we're going to use a simple, real-world picture to build our intuition first. Okay, I want you to picture this. A long street with a perfect row of mailboxes. They're all the exact same size, they're sitting right next to each other in an unbroken line, and every single one has its own unique number painted on the side. Got that image? Good. That simple idea is the absolute key to understanding arrays. And that brings us right to the formal definition. See, an array is just like that row of mailboxes. It's a data structure that holds a bunch of items, and they all have to be the same type, in what we call contiguous or side-by-side spots in memory. And trust me, that side-by-side part, that's everything. It's the whole secret.
So that street of mailboxes is a nice analogy, but how does it actually exist inside your computer's memory? Let's peel back that idea and look at what's really going on, the technical details.
Okay, so think of your computer's memory as this gigantic grid with an address for every single spot. When you create an array, the computer finds an empty block and it just remembers the starting address. Let's say it's address 1000. And because every item in that array is the same type, it knows they all take up the exact same amount of space, maybe 4 bytes. So if the first item is at 1000, where's the next one? Well, it's got to be at 1004. And the one after that, 1008. It's perfectly predictable. There's no guesswork at all.
Now, that mailbox number we talked about, it has a technical name, the index. It just tells you the position of an item in the array. And here's the one thing that trips everyone up at first. In pretty much every programming language you'll use, the first index is 0, not 1. So why do they do that? Well, it's because the index isn't really a counter, it's an offset. It's asking how many steps do I need to take from the starting address. So to get to the very first item, you take 0 steps. Makes sense, right?
This perfectly neat and tidy system gives arrays a kind of superpower. But, and it's a big but, it also comes with a major weakness. And this isn't just a list of pros and cons. This is one of the most fundamental trade-offs you make as a programmer.
So what's so interesting here is how these two columns are basically fighting each other. On one side, arrays are incredibly fast and efficient with memory. Because all the data is right next to each other, your computer's processor can just blaze through it. But on the other side, they're super rigid. They have a fixed size, and trying to change things in the middle, yeah, that's a real pain. Let's break that down a bit more. The biggest advantage, the superpower, is something we call O1, or constant time access. What that means is because the computer knows the starting address, the size of each item, and the index you want, it can do some super simple math that jump directly to that item's location, instantly. It literally doesn't matter if the array has 10 items or 10 million. The time it takes to grab item number 5000 is the exact same. That is ridiculously fast. But here's the trade-off. What if you want to add a new mailbox right at the beginning of our street? You can't just plop it down. You have to physically pick up every single other mailbox and shift it one spot over to make room. This is what we call an ON operation. The time it takes is directly related to N, the number of items in the array. The bigger the array, the longer it's going to take to shift everything. So here's the bottom line, the key takeaway. Grabbing data if you know its index, lightning fast, O of 1. But pretty much everything else, searching for a value, adding a new one, or deleting an old one, means you might have to go through that slow, one-by-one process. That's the engineering reality of using arrays.
Okay, I know this might all seem a little abstract, but here's the cool part. You are interacting with arrays right this very second. So let's look at a really powerful real-world example that shows just how critical this structure really is. So far, we've only been thinking about our street of mailboxes, which is just a single one-dimensional line. But arrays can get more complex. They can also be structured in 2 dimensions, like a grid with rows and columns. And when we do that, we often call it a matrix.
And this is where their power just explodes. A one-dimensional array is basically a list. But a 2-dimensional array, that's a spreadsheet. Or even better, it's the grid of pixels that makes up a digital image. Every single pixel you're looking at on your screen has its color value stored in a massive 2-dimensional array. And the whole reason your computer can update millions of those pixels fast enough to show you smooth video is because of that O1 lightning-fast access speed of arrays. So look, if you take only one single thing away from all of this, let it be this simple phrase. This is the absolute core identity of an array. Its incredible speed comes directly from its rigid, neat, side-by-side structure. And its inflexibility? Well, that's just the price you pay for all that performance. Which of course brings us to the next big question, right? What happens when that trade-off just isn't good enough for what we're trying to build? What if we need to add and remove things all the time? Is there some other ways, some other structure that can give us more flexibility? Well, we'll explore that very question next time.